Right, good afternoon, everyone. By this point in the conference, you've all heard compelling stories. Every great story always comes with a hero and a villain. And today, we group four are telling you how we fought through one of the most critical villains of our time, decarbonizing the industry. Unlike other sectors, industrial processes are energy intensive in its very nature. The extreme conditions and environments needed to make steel, especially, emits a lot of carbon emissions to up to nearly a quarter of all global emissions. Carbon isn't just emitted from burning fuels. It is usually integral to part of the chemical processes. So that's where we step in today. My name is Anthea, and with my brilliant colleagues here, we're telling you how we've created tools and strategies that can turn this around. Not only have we focused on the well-established industry so far, we've also tapped into the opportunities in the developing world, not to miss any, making sure it is a just transition. Right, so if I could pass the mic to Aiman on my right here, who will tell us more about the industry in the United Kingdom.
Hi, everyone. I'm Aiman. Hi, everyone. I'm Aiman, and my research is focused on the very country we're sitting in right now. Yes, let us begin this presentation with the UK's industrial sector. The industrial sector in the UK produces about 14% of the country's greenhouse gas emissions. And to cope with this, the government has introduced a variety of policy mechanisms like contracts for difference and grant fundings. At the same time, the UK has set ambitious goals and targets, like creating the first net zero industrial cluster by 2040 and producing 10 gigawatts of hydrogen by 2030. But with such ambitious plans come an important question. How does this evolving policy landscape impact company-level decision-making, and how does that all translate into emission reductions? These policies are also quite cluster-centric, which is why I've used Humber cluster, the largest emitting cluster in the UK, as my case study, to see what policy combinations works best for a cluster. Now, at the same time, the cluster chemistry and opportunities also play a vital role in policy effectiveness, which is why I've added this bar graph here to show that within Humber, power sector produces highest emissions, followed by iron and steel, and then refineries. Some food for thought there. Now, to capture the complex interplay of diverse policy mechanisms, available technologies, and heterogeneities of industrial firms within the cluster, an agent-based model was produced that takes into account three major categories of inputs. The first is the distinct characteristics of industrial agents. Second, the energy and carbon price projections. And third, most importantly, the user-defined policy scenarios. Now, the model gauges the feasibility of a low-carbon technology transition for each industrial agent based on the maximum net present value that incorporates the price of avoided carbon, as well as the financial benefits of policy mechanisms. The model outputs includes clusters emission profile, energy infrastructure requirements, required policy value, and also some information about cluster's own contribution to that policy cost. Now, let us now move on to the analyses and look closely at the blue and green hydrogen adoption in the cluster. Now, testing different revenue support scenarios, as you can see in the bar graph, for blue and green hydrogen leads us to three main conclusions. The first being that the offshore wind source green hydrogen becomes cost competitive with blue hydrogen at much lower revenue support levels as compared to grid source green hydrogen, which is why these two highlighted hydrogen combinations works best for a geographically advantaged cluster like Humber. However, when you talk about a sustainable funding framework, increasing the policy cost, even though it increases the hydrogen adoption, it reduces cluster's contribution to that cost. This brings us to our third conclusion on the need for a balance between emission reductions and cluster's policy contribution. All these insights were then fed into a broader illustrative policy strategy for Humber that I'll be defining in the next slide. Now this effective and sustainable policy strategy was designed for Humber, as you see in the table. That includes tailored revenue support values for blue and green hydrogen. It includes carbon contracts for support for industrial carbon capture, 12% free emission allowances reduction, and necessary planned fundings for electric arc furnace adoption in Humber's steel sector. Now, this policy mix can reduce cumulative emissions by an additional 21 megatons of CO2 from the policy scenario, but This is subject to timely CCS and bid infrastructure availability. As you can see on the graph on the left, that while residual emissions in both scenarios are quite close to each other by 2050, the early adoption of low carbon technology is what truly drives emission reductions. This reduction requires a policy cost of 2.7 billion, the villain in the story, as Anthea just mentioned. However, 42% of this cost can be contributed by the cluster itself by payment of levies through electricity and gas demands of the cluster and through carbon taxes on scope 3 emissions. Similarly, the model shows that a 600 million grant funding to Humber steel sector can sufficiently incentivize electric arc furnace adoption. However, to accommodate the increasing electricity demand, we need to incentivize and accelerate grid infrastructure development in the cluster. Subsequently, this leads us to our recommendations for the three major stakeholders of the research. For the government, the research highlights the need to embrace more sector-specific policies, prioritize rapid infrastructure development for CCS and electrification, also improve the visibility of scope 3 emissions for a sustainable funding framework. Industries, on the other hand, should further emphasize continuous technological innovation. And for the researchers, the model provides a comprehensive toolkit to further analyze the emerging policy mechanisms, such as the carbon border adjustment. So in conclusion, the model provides a granular and a realistic perspective of UK industrial policy implications for Humber, offering transferable insights for other industrial clusters. Now that's it from my side. Next up in our presentation is the neighboring region argued to have more stringent net zero targets than the UK. I would like to call Estelle to discuss European Union's hydrogen policies.
Thanks, Aiman. Iron, steel, cement, chemicals, refining, all these industries use hydrogen. The problem is that today it is much cheaper to produce hydrogen through the polluting method of steam methane reforming than through electrolyzers using decarbonized electricity. The European Commission implemented policies to make clean hydrogen cost competitive with natural gas by 2030. I'm Estelle Vafiades, and my research aims to assess these policies to see if they can generate sufficient demand pool within the industrial sector and when cost competitiveness can be achieved. To do so, I designed a market penetration model. This model takes 4 inputs: the quantity driven by current policies, the current clean hydrogen cost, the technology learning rates, and the estimation of future natural gas costs. And this model gives 2 main results. On the one hand, the estimation of future clean hydrogen costs and their cost competitivity. On the other hand, the needed learning rate to achieve cost parity associated with the probability of reaching them based on the literature. This model has been applied to 72 scenarios on hydrogen and 3 natural gas costs. 5 main results came from this analysis. First and foremost, there are not enough demand pool policies. Demand pool policies drive 222 for less quantity than supply pool policies. This graph speaks for itself. In green, you have the target of 10 million tons of hydrogen production set by the European Commission in the hydrogen strategy. You have the current quantities driven by current policies. As demand pool policies are so far from what is needed, the rest of this context will only focus on supply push policy control. The second main result is that hydrogen will not be cost competitive with the low natural gas costs. On the 72 scenario assessed, no one reaches cost parity of hydrogen with a natural gas cost of 16 euros per megawatt hour, the low cost estimation. Natural gas cost has to be at least at 31.5 euros per megawatt hour if we want to get a chance to achieve cost parity between clean hydrogen and natural gas by 2030. The third main result is that the needed learning rates become realistic only under a high natural gas cost estimation. In that case, it can even reach a probability of 73% success against only 57% maximum with a reference natural gas costs. Last but not least, the two last results are that a 100% on-when electrolyzer scenario and on-site renewable electricity production lead to cheaper hydrogen. Combined, they make hydrogen up to 60% cheaper than in any other scenario. In light of the above analysis, this assessment resulted in the recommendation for the European Union to support projects with PEM technology and projects with on-site renewable electricity to feed production, feed the electrolyzers. The European Union should also associate the current EU ETS schemes with natural gas taxes to ensure that natural gas taxes reach high estimation. The money raised from these taxes should be used to fund more demand pool policies on the long term, such as contract for difference, for instance. Now I let Ari explain us what is more specifically needed to decarbonize the iron and steel industry.
Thank you, Estelle. Hello, everyone. My name is Harry. So today I'll be presenting you with my research on how to accelerate the uptake of clean technologies such as carbon capture and hydrogen in the iron and steel sector. And now let's start with the background. So just as Anthea already mentioned earlier in the intro, iron and steel sector contributes one of the most major CO2 emitters among other industrial sectors. And with over 70% of the existing steel plants are still using the blast furnace or BOF methods, which is very carbon intensive. And out of all the challenges we currently have right now, the main challenge is always with the high cost of transitioning to cleaner steelmaking methods. Well, the solution, one of many solutions that is actually to implement the acceleration of demand pull policies, just what Estelle mentioned earlier. However, we still have a gap for this. The first one is actually the demand pull policy research around the globe right now. It's focusing on the technological part and qualitative part of the assessment. And they are also country specific and lack global focus. So in this case, in my research, I focused on the global perspective by analyzing 385 steel plants across the globe, spread over 40 different countries. In this case, I also developed a model which can analyze whether the current policies are sufficient or not, and design an optimal policy frameworks for each steel plants and in each country. Now let's start with the methodology. It's pretty much simple. In this case, I start with the data gathering. Here I collected demand pull policies from ETS, carbon tax, incentives, and grants with all the data related to the steel plants itself. Then I developed a novel market penetration model using the software WhatSpace with the objective function to maximize the policy-induced market share. Here, I focus on 6 different pathways from IEA, ranging from integrating the carbon capture technology to the existing blast furnace with the electrification using green hydrogen methods. Before I show you the results, I want you to look at the map here. This is actually one of the results of my steps of my research. I collected the data for every demand pull policy currently in place in the iron and steel sector in 43 different countries. You can see here, most of the countries already implemented policies like ETS, incentives, grants, or carbon tax. But the main question is, are they really sufficient to drive net zero transition in the iron and steel sector? And how can we actually measure that? Well, I will answer the questions in the results. Now, if you see in the results on the left chart, this is actually showing the existing demand pull policies evaluation based on the total policy induced market share. If the total policy induced market share doesn't reach 100%, it means the policies are actually insufficient to drive the clean transitions. And therefore, it is required for us to design an optimal policies, in this case, to reach that 100% value, and also to make a balance of the costs between the industry and the governments. But how much is actually the total policy implementation cost? Well, In this case, it will differ based on the scenario. So in this case, for example, for green hydrogen is actually the most expensive, with a staggering $434 billion per year investment required to decarbonize the sector, which is very expensive. And therefore, it is really required for us to implement not only a single policy, but a combination of policy and also multiple pathways of steelmaking technology, which is cleaner, is also required for this purpose. And if you can see the pattern here, actually the cost for industry is always higher than the cost for the government. So that is actually what I will discuss in the recommendation sections here. So I will present you with a threefold of recommendations for the governments, industries, and researchers. For the governments, we know that the existing demand policies are insufficient, and therefore it is required for them to have a more balanced mix of policies and to propose sustainable financing mechanisms. This could involve green financing or public-private partnerships. For the industry, it is necessary for them to do the cost optimizations for research and production efficiency and partnership with the government. And as for my model, it's focusing on the quantitative impact on environmental policies. It can always be expanded into a multi-year scope, and not only for steel industry, but can also be applied into other hard-to-abate sectors. Now, my colleague Anthea will actually do one of the recommendations for the industry part. Her research is interesting as she will focus on the open source energy modeling system for the iron and steel sector in Japan.
First of all, thank you, Harry. Government intervention is indeed an extremely powerful tool to be part of the decarbonization of the steel sector. However, I'm here today to stress a different angle. I and my research believe that the industry has the most responsibility in this part. Let me now talk you through my research that sheds light on the techno-economic details of the steel sector itself for the case of Japan. Over the past few months, I've had the opportunity to work with Transition Zero to build a specialized version of the model Osmosis, which I termed the Osmosis steel. Current energy models that can be translated to represent the steel sector are either data intensive, require upfront financial cost or burden, or require complex assumptions. I've made an open source osmosis steel model that is accessible for you all, that can be specialized to model the technicality of steel production. This is a map of Japan. Markers being currently existing steel plants, colors being the size or we say nominal capacity of the steel plants itself. Obviously, I've chose Japan to test my osmosis steel model. Reason being that Japan is the third largest steel producer on earth, but it's still 75%, very higher, reliant on coke-based blast furnace methods. So when it comes to osmosis steel, what is it? Well, it is built in a pivot environment. The system boundary of the model covers the entire steel production process, from upstream material supply coming into a steel plant to in-house steel production through all the equipment, and then final steel demand being met while also considering policy targets. If we look on the left here, when we see the block of data collection, a variety of data are obviously fed into the model, which includes Japan-specific asset data, the capacity of the plant, the operating statuses, the retirement dynamics, and the cost of them, emissions intensities of each production route, as well as other financial metrics. All of these are fed into the automated run of the model, and then it's optimized for the minimized least total system discounted cost to give us the set of output variables on my right here, which spans from carbon emissions in an annual basis, technology, aspects of technology, and costs, of course. So before I dive into the most exciting part of my presentation, I must notify everyone in this room that my model is now on GitHub as a repository. So if anyone wants to collaborate and access my model, please contact me or Transition Zero so that we could discuss further. Right, on to the first set of actual results, commodity price forecast. All commodity prices which are used to make steel, let's say, are expected to rise through 2060, only exception being imported green hydrogen and clean electricity in Japan, meaning that we are in a good scene set for Japan to decarbonize its steel sector if we just look at the operating variable cost itself. Next, so what actually do we need to, what technology method or production pathway are we using to make steel? Towards 2060, we say that the direct reduced iron, DRI route used in an electric arc furnace is key in replacement of the current blast furnace speeds. I must note that in order for this to happen, all the blast furnaces in Japan should be phased out by 2060, meaning they should retire. And in those transitional years in between, 2030 to 2045, we need transitional technologies. That means we need to inject hydrogen into current blast furnaces in order to keep Japan on track with its already announced national targets. So what does achieving the mix in the previous page give us? Well, in the most optimistic scenario, we can reach up to a 57% CO2 reduction by 2060. Well, this is promising, but it only brings us close to the IEA target of 60%. This means more ambitious acts have to be in it. To incentivize all these changes, the current Japan carbon tax of around $2 per ton of CO2 is nowhere near enough. Osmosis Steel has suggested a marginal carbon price, a dynamic one, in range of $80 to $240 per ton of CO2 in order to give the right economic pressure for the steel sector to make changes. And inevitably, when we say changes, we mean additional costs. In my model, you can see up to a $40 billion additional cumulative investment needed by 2030. That's a huge amount. That will also double the liberalized cost of steel by to up to $800 per ton by 2060. But note that here, only a 3% cost transfer is seen to the end-use products that use steel. Well, I mentioned that hydrogen will become a key commodity in the new mix of steel production routes. According to several scenario analysis that I've conducted, the most combination of hydrogen uptake policies that have to be in place are an import cap or on the price or volume of imported green hydrogen into Japan, plus subsidy for electrolyzer in order to incentivize the Japan steel sector to build in their own electrolyzer to make hydrogen for steel. To wrap up, we must all note that decarbonizing the steel sector is not a policy target. It is a collective effort that should be borne the most by the industry. Right. Now, let me pass on to Bomi on my right here, who will tell us about case study in a country far off from Japan, Nigeria.
Thank you, Anthea. Hello, everyone. Have you ever wondered what the decarbonization pathway for a developed economy like Nigeria would look like? Well, I'm Bomi, and today I will show you. Now, Nigeria has big goals, both economically and from a climate mitigation point of view. Economically, we're not doing great. The unemployment levels and inflation levels are both 30% as we speak. And the industrial sector verified as a key sector to change that trajectory. Simultaneously, Nigeria has big climate goals. We plan to reach net zero by 2060. And we also got a bunch of smart consultants to draw up our energy transition plan. And the industrial sector is the fourth largest focus area and is to decarbonize by 80% by 2050. Now the key research question begins to emerge. How do we support this transition? How do we understand this and what pathways can we follow? The Lekki Free Zone on the right has been chosen as the case study for this research. It's the largest industrial cluster. It houses the Dangote refinery, which is the largest single train refinery in the world. But we see something interesting as we dive into this cluster. We see there's a heterogeneity in terms of the players. We have refining, we have automotive assembly, and we see a lot of light industry from things like wig, cosmetics, and even furniture. How do we address this? Now, just like my colleague, I followed an agent-based model. And the reason is to be able to capture the granularity of the individual players. Because what the decarbonization for refining looks like is very different from what it looks like for furniture manufacturer. On the left, we see the data inputs, and we use raw energy prices. And for industry data, I want to quickly highlight that this was a key challenge. So we used analogous industry data, and we had to get the map data and also assume to the policy levels. In the middle is the model itself, and the key decision framework is around the net present value of what the sub-process transition would look like, taking into account the value of avoided carbon, the cost of the current technology being used, and the cost of the transition sub-process. The range of results are generated on the right, as you can see. The very first result I want to highlight is just to begin to understand by how much of an impact can decarbonization of the industry sector look like. And we see that on the left, in the do nothing scenario, emissions from that cluster is expected to rise by 10% over the 27-year period. And on the right, in our model scenario, where we begin to actually put in low carbon infrastructure and low carbon technology adoption, we can achieve up to 93% reduction in emissions in comparison to the business as usual. Now, if you look at the right, you see that there are two key years where things begin to actually happen, and that's 2030 and 2041. So the second and final result that I'd like to show you is just begin to illustrate what is the snapshot of the trajectory. What does that look like for the cluster? Again, on the left, on the do nothing scenario, we see that by 2047, actually, by doing nothing, some sub-processes begin to transition to low carbon. And then we see that in three industry subgroups, that's the light industry, vehicle assembly, and oil storage. And it's by 2047 that electrification and solar become competitive. But clearly, we cannot wait that long. And in our model scenario, we see that by 2030, there's a range of sub-processes across all of the subgroups present in the cluster begin to make that transition. And the latest transition happens by 2041, which is when we expect CCS to become competitive. Now, to conclude, again, our three focus areas is the government, the industry, and research. And the key villain in this is the huge gap in terms of emissions reporting transparency, and actually implementing foundational things like carbon budgets. And that's where we need the government to urgently start to make strides in that area. And for industry, is begin to think of creative financing mechanisms like public partnership and accessing green financing to begin to make this low carbon transition happen. And for research, with this model, we can see that we can actually begin to understand what industrial decarbonization will look like. So it's just to build in what actual data and to actually refine the model to be more representative of the cluster. Now I'll hand over to my colleague, Batoul, who will take us to another part of the world to another interesting case study. Thank you.
Thank you so much, Bomi. Oil, decarbonizing oil. Is that even possible? Well, for Saudi Arabia, that's the plan. I'm Batoul. I come right from the Middle East, witnessing the impact of Saudi Arabia and oil on the region, and joining it with my passion for political economy. I unpacked it all for you. First, let me take you with a quick background about Saudi Arabia. It's a very heavily oil-based economy, and the state-owned oil company is among the 6 fortunes worldwide, continuously. Well, that's not the full story. What sets Saudi Arabia apart as well is its centralized monarchical government with a majority of the power held within the royal family. Not only that, but also the market is centralized, with the top companies in the country are state-owned. Since we are dealing about the transition of an entire economy, I decided to adopt the co-evolutionary theory. This maps the space on a micro, meso, and macro level and identifies 5 systems that co-evolve together and influence one another. Policies have been studied enough. Today, I'm adopting a bottom-up approach and seeing how firms, through business models, can access the market value. Actually, business models are a combination of these two systems, and their interaction with the rest of the systems is characterized as viability, feasibility, and desirability. I particularly chose to study the viability of business models using this value pool modeling approach. Why? Because once I have proved the presence of the money in the market, once I have proved the market sizes, this will automatically attract the private sectors and eventually investments. And this is what we want, right? Market sector, market side, participation, demand side, participation. Let me give you an example. Once we have proven that the utilization technologies such as enhanced oil recovery and blue hydrogen are profitable, then the business models will be interested to come and capitalize on these opportunities. Well, as much as we were interested to assess the commercial opportunities and quantify them, we couldn't complete totally the model. This is particularly due to the absence of robust data. There were actually, and most importantly, there were not comprehensive national strategy. Of course there were, but most of them were only accessible from the newspapers and not always consistent with one another. But most importantly, the second reason for that is that there's no carbon price. There's no cap on the companies, and hence there's no incentives for reduction, and eventually no demand on carbon reduction or capture. Well, but Saudi Arabia still wants to transition its economy. What can we do? Then, since I'm dealing with a co-evolutionary approach, the co-evolutionary theory of these 5 systems says that whenever we make a change in one of the systems, it exerts pressure on the entire system. That's why, and leveraging the position of Saudi Aramco as a top research and development in the field, I decided to tap on the technologies and institution systems. Particularly within the technologies, I recommend deploying CCUS infrastructure, particularly transport and storage, because this will create market signals of technological readiness and will achieve cost reduction through shared infrastructure. But I particularly emphasize on the importance of implementing and deploying carbon utilization technologies through research and development or technology transfers. This is particularly important as it will be commercializing the captured carbon that will be used as feedstock for commercial products. Finally, I recommend opening CCUS projects for public-private partnership. Due to the incumbent nature of Saudi Aramco and its monopoly in the market, it's really impossible for the private sector to come and act in the market. And anyways, who want to compete with Saudi Aramco? But most likely, you might want to invest in it. Thank you.
Thank you, Marie. So, to make a long story short, the 6 previous presentation showed us that the super government can help super industry to overcome the cost supervillains and the other obstacles to industry decarbonizations. But this can only happen at 3 conditions. First, super governments need to implement more demand pool policies, including policies addressing prices. Second, super governments and super industry need to deploy more specific infrastructure. And finally, super government and super industry need to plan a long-term sectoral budgeting that starts now. Thanks for your attention. If you have any questions, please answer now or comment here at your podcast later.
Thank you very much. A real tour de force of a very diverse and challenging topic, which lies at the heart of decarbonisation. So thank you. One area that I was wondering about is trade. Clearly, global warming is a global problem, and industrial consumption of energy is also subject to the geographic pros and cons of the specific location where it's happening, as well as the particular government policy. I just wondered whether any of you have any comments on, with things like carbon border adjustment, stuff like that, what how these things may also drive the evolution of industrial demand around the world, please.
Yes. Thank you for your question. Okay, so regarding carbon border adjustment mechanism, yes, that's like a very interesting policy mechanism that's like emerging. And European Union is about to implement it in 2026, which is also, I think, one of the reasons that in the UK, for example, I can say for the iron and steel sector, because EU is currently going to implement this mechanism for iron and steel and cement. And for the UK, like the iron and steel, UK is actually the largest exporter of iron and steel to the EU. And of course, this mechanism is going to impact it, which is why I think currently the iron and steel sector is also very much interested in accelerating decarbonization within the industry. And this is also one of the reasons I believe that, for example, Tata Steel and the British Steel within the UK are under negotiations within the government to see if they can get some grant funding for electric arc furnace adoption within their sector. So yes, so yeah, like especially for the UK, I can speak for the iron and steel sector that it is definitely driving decarbonization within the UK.
Just to touch on quickly. So the Dangote refinery is a new refinery, and the capacities are both Nigeria's consumption. So they have an export focus as well. And one of the things that they're looking at is carbon capture, because they understand that in a system where there is carbon border adjustment mechanism in place, they need to be compliant. So it's something that cuts across globally. And also, as refineries begin to reach their end of life in Europe, they also expect to leverage on that. And that's why it's also a key focus for them, trying to decarbonize as well. So yeah, it's something we looked at in our research, and they came up trade is a very important component of industry.